we have looked at different aspects of superconductivity, starting from the microscopic theory and type 1, type 2 superconductors, and what is the specific heat behavior, thermodynamics of superconductors, magnetic response of superconductors, and the different effects like the Josephson junction effect shown by superconductors. Now we will have a few lectures which will be based on types of superconducting materials which show superconductivity. So this will be just a brief overview giving you broad general classes of superconductors. It's a very vast, I mean there are new superconductors being discovered every day. It is not possible to cover all different types of superconductors, but I will try to give you a flavor of what are the different broad general categories and what is something interesting about some of these superconducting systems. So let's begin. So in terms of superconducting materials, one has very diverse type of superconducting materials, and amongst the elemental superconductors, you have this is a periodic table where the colored square shows the materials which are superconducting, and you can see that a lot of the elements in the periodic table are superconducting. Okay, what is shown in yellow are materials which are superconducting under normal conditions, and what is shown in green are superconducting materials which become superconducting under high pressure. For example, here you can see that lithium, for example, becomes superconducting with a critical temperature of 20 Kelvin at 50 gigapascals of pressure. Okay, whereas beryllium Be, for example, has a Tc of around 26 millikelvin and 9.95 Kelvin actually in film form. Okay, so the upper Tc is for bulk. Okay, and if it is under the form of a film or something, then it shows under certain conditions it can actually show in the form of a film. It can have a Tc which is relatively high. Okay, so you can see that elements can actually be superconducting either in normal conditions or under certain sort of material processing and so on. The material can become superconducting or under high pressures. Okay, and there are certain materials which actually have avoided becoming superconducting. The answers are still not known, but there are certain materials which actually do not conduct. For example, gold, for example, it's very good conductivity, but unfortunately there is no known demonstration that it becomes superconducting. Certain materials, if you make them into nanoparticle form, then actually they start conducting. They become superconductors. So there are a number of examples that you will find when you take the material in a very small nanoparticle form, the material can become superconducting. So these are as far as elements are concerned. Some elements which are superconducting, there are quite a large number of them which are superconducting. How about compounds and alloys? Okay, and there are very large number of these compounds and alloys which actually superconduct. So for example, you can have niobium nitride or Nb3Ge, which have pretty high TCs of 15 Kelvin, 23 Kelvin, and these are actually strongly type 2 superconductors. The critical fields are actually pretty high, about 10 raised to 5, about 10 Teslas or so, and these were discovered in 1940s, 1971. And then there have been a very large different type of materials called ceramics, whose TCs have continuously shot up. Okay, I will come to these a little later. I will discuss specifically about these type of materials, but you can see that these have been discovered in the late 80s and early 1990s, and the TCs have shot up from around 35 Kelvin to 150 Kelvin. So these ceramics are these materials which have copper and oxygen inside them, have pretty complex chemical structure, chemical stoichiometry, but they have very high TCs. Okay, so as far as the types of materials which which show superconductivity, there are a large variety of them which are seen. For example, this view graph actually shows you the temperature, the superconducting transition temperature as the function of year. I have taken it from the internet. It shows only up to 200 2010, but you can see that there is a very large diverse type of materials which have been very periodically discovered. And here across on this side you will see the temperature scales. For example, here is liquid helium temperature, liquid nitrogen temperature, liquid neon temperature, surface of Pluto, liquid nitrogen, night on the moon. Okay, what are the typical temperatures that are available, for example, on the moon surface, okay, at night. So these are the temperatures that you have, and there are different materials which actually have been found periodically over a period of time, and the critical temperature for them has continuously risen up. For example, here you see a very important material, MgB2, okay, which was discovered sometime in the early 2000, and it has a pretty high critical temperature of 40 Kelvin or so, close to 40 Kelvin. Magnesium and boron, it is made by magnesium and boron. It was there in everybody's lab, because magnesium is quite cheap, boron is also quite cheap, but nobody thought of putting them together, but it was done, and they found that it has a pretty high temperature. It has very interesting properties. This is a C60 potassium based C60 compound, which was found in the late 1990s, and C60 compound, as you know, is a buckyball compound that itself shows superconductivity with potassium, of course. And this material also becomes superconducting. And then there are a whole lot of diverse variety of materials. Here you can see boron doped diamond with boron doping. Films of these diamonds actually become superconducting at liquid helium temperatures. Okay, and that was pretty recent, and in fact still research is going on these boron doped diamond films and their superconducting properties. And on this end here you can see that in the late 1980s, suddenly, whereas all the other materials were showing moderate temperatures which increased to about 35 Kelvin, suddenly there was a huge jump in the transition temperatures with the discovery of these ceramic based materials. And these ceramic based materials gave rise to the birth of superconductivity, where high temperature superconductivity, where people really started thinking that now it is possible to discover superconductors working at room temperature. That dream has still not got realized. There have been periodic sort of new discoveries being made regarding room temperature superconductivity, but they have not really stood test of experiments to really prove that they are superconducting at room temperature. For example, here you can see this mercury based high temperature superconductor has a critical temperature of around 150 Kelvin at under 30 gigapascals of pressure. This is of course very high pressure, but it is showing that there are routes to reaching high temperature superconductivity or room temperature superconductivity. Around this end, on this end, after 2008 onwards, there has been a new line where there are these iron arsenide based superconductors which have led to new excitement, where there has been a substantial increase in TC, not as high as high temperature superconductors, but still nonetheless there has been a new route towards discovering higher temperature superconductivity, where TCs have pretty high TCs have been reached using these iron arsenide compounds. Okay, so the search for high temperature superconductivity continues. In fact, just a few years back, very close to room temperature, there have been reports of course, these are very well verified reports, that hydrogen sulfide, which is a gas, okay, if you pressurize it, if you apply very high pressures on this hydrogen sulfide, then this hydrogen sulfide actually becomes superconducting with transition temperatures which are close to room temperature. It is just below room temperature. They have not yet reached exactly 300 Kelvin. So if I remember, or if I recall, the critical temperatures are close to 200 Kelvin, but these are pretty high transition temperatures. The only drawback is that you require very high, few gigapascals of pressure to be applied to this gas, and the system then starts superconducting. Okay, but it is under very high pressure. okay, but it has a possibility, and this was again has led to a major new excitement, that you can have systems which can be superconducting. These type of materials, for example the ceramic superconductors, are non-BCS type superconductors. They typically have very high TCs, and their superconductivity or the transition temperatures and their behaviors are typically not explained by conventional BCS theory. The mechanisms are different. I will tell during the course a little bit about them as we go along, but not too much, because these are still being, one is still trying to understand the physics of these systems. Similarly, there are other systems which do not always follow BCS type, but the example which I told you about high TC about hydrogen sulfide superconductors, which superconduct at very high temperatures under the after you apply very high pressure on them, on these systems. This sort of material actually is superconducting at such high temperatures, and the amazing thing about them is that the superconductivity follows BCS type behavior. Okay, the behavior of these high temperature superconductors can be actually be explained by BCS theory. So it is one of the major successes that that the BCS pairing mechanism is reasonably strong to allow you for such strong coupling to survive at room temperatures, because BCS theory basically tells you the strength of Cooper pairs, the strength of coupling which is going to bind this pair of electrons and generate Cooper pairing, which is responsible for superconductivity. And the fact that this pairing survives up to such high temperatures tells you that the pairing is very strong. Earlier it was believed that BCS theory cannot give rise to such strong pairing between the particles, and the pairing will break by around 4-5 Kelvin or so, that the thermal energies are typically of that order that they can actually lead to breaking of this phonon mediated coupling between these electrons. Okay, however, it turns out that even at such high temperatures as in hydrogen sulfide, the BCS theory works reasonably well to explain the behavior of these systems. Okay, so these have been some major ideas and surprises which have kept the kept the race actually for search for high temperature superconductivity ongoing, and the phenomena remains as a mystery till date. Nobody fully understands where does high temperature superconductivity really come out from, and so there is continuous new discoveries being made in this area. So these are different materials which exist. Now, from the application point of view, things like the discovery of niobium 3 tin became very important, because it was found that it has a TC of around 18 Kelvin and has an upper critical field of 24 Tesla. Now, what is important about this niobium 3 tin system NB3SN is that these material can be drawn into wires, okay, whereas the ceramic materials are not convenient to be made into wires. A lot of different processing has to be done to make them into a wire like form. These are of course strongly type 2 superconductors. These high temperature superconductors are strongly type 2. They have very high critical temperatures and critical fields. However, one drawback is that you cannot make them into wires. But niobium 310 has a moderately high temperature of our critical temperature of 18 Kelvin and pretty high BC2 upper critical field. The advantage from application point of view is that niobium 310 can be drawn into wire-like forms. Okay, and as a result of which this material has found huge amount of application in making superconducting magnets. Nor mostly all superconducting magnets are wound with this niobium 310 wire. They allow you to actually send in a lot of current with very low loss, and you can reach very high fields, because this superconductor turns normal only above 24 teslas. You can use this to make very high field magnets of few tens to few tens of teslas. Okay, you can use niobium 310 to design magnets which can operate up to few tens of teslas. They are unlike electromagnets, they don't generate heat. Okay, because you are not using copper, a normal metal which is going to heat up when you send in large currents. These can take in few hundreds of amps of current, okay, and generate no dissipation. Okay, so this for magnet technology has received a big boost. You because of the discovery of this niobium 310. And there are some similar type of materials which have been used for magnet winding, but niobium 310 remains as a very popular choice for making magnets. Recently, people have begun processing these high temperature superconductors with complex processing technologies. They have come out with cables which are made up of these high temperature superconducting wires, which people think if you can cool these wires with liquid nitrogen. So they have these wires in the core which are made up of these high temperature superconducting materials, and you circulate liquid nitrogen around them, so it will make these wires actually superconducting. And such complex cables which have a coolant and a wire inside it are thought to be used for applications for carrying currents to homes and so on. Such experiments have been going on in Japan to try and see the cost feasibility, whether it is feasible actually to do such things, where you can over kilometers make such cables where you are going to circulate helium nitrogen through these wires, liquid nitrogen through these wires, and inside them have these superconducting cables. Okay, the cost has been not very, I mean, it is there are a lot of issues, as you can understand, having such complex cables compared to this a simple wire which is going to carry current. So there have been issues from the practical point of view in implementing these high temperature superconductors for application. So the real sort of breakthrough which is needed is to have superconductors which are operating very close to room temperature or at room temperature, and to have the materials be such that you can draw them into wires. If you make powders and so on and so forth, a very ductile form of material, if the material is very brittle, for example, for like these ceramic superconductors, then you cannot make them into wires. The moment you try to make them into wires, they break and so on. So from the practical aspect point of view, even if they are high temperature superconducting, if you cannot make it into wires, then of course there is no application, or there is not much application you can have out of them. So you have a very, very vast variety of materials which are available, and I will just discuss a few important aspects of some of these materials.